All right, let's start. So before we start today's lecture, any question about the first assignment? Any quick question? All right. So if you have any question, or you can ask online, and you still have like 5 days to do the first assignment. Yes.
Can you substitute the library with the MATLAB internal library for SVN?
Sorry, what did you say?
Can I substitute the lib SVN with MATLAB's own SVN?
Yes, it's okay. If you just want to compare with another third-party SVM library, you can say use MATLAB's SVM. That's okay. You don't have to compare with libSVM. I said this in the course forum. Any third-party SVM, it's okay. I just want to compare your implementation with, those off-the-shelf implementation, just to verify your implementation should be consistent with any third-party library. Any other question? No? All right. Okay, so that's good. Let's start today's lecture. So we now have covered quite a few topics, but most of them are, on supervised learning, right? Last week we talked about PCA and LDA. PCA is unsupervised learning, and LDA is supervised learning. So as you can see in machine learning, in the for most of the real-world applications, we might use labeled data or unlabeled data. If you have labeled data, then pretty much you can just formulate the problem into supervised learning. But if you only have access to unlabeled data, then in this case you have to use unsupervised learning. And today we're going to talk about one very important category of unsupervised learning. It's called clustering, right? So in contrast to classification, clustering is unsupervised learning. And actually, in real world, we have many more unlabeled data than labeled data, right? So with the, in most of the cases, you can even access to infinitely many unlabeled data, like a web page, for example, right? You can, just cloud billions of, web pages, but you don't have the label. So what we can do with those unlabeled data, right? Okay, so that's the purpose of unsupervised learning. So we can, for example, using PCA, which is also unsupervised learning, to reduce the noise, to extract useful features, to reduce the dimensionality of the data, such that you can later, reduce the computation complexity. It's often used as a pre-processing step for the next, for example, training a classifier, right? Okay, so the so-called clustering is, we want to discover groups such that the data samples within a group are more similar to each other than samples across group, right? Just recall, last week we talked about linear discriminant analysis. This is actually one of the criteria for LDA, for linear discriminant analysis, right? So recall that for LDA we have two criteria. One is to make the distance between class, within a group, become small, right? at the same time, we try to maximize the distance between classes, between groups. Here, we don't have the label, but we try to assign the data into different groups such that within a group, those data points look similar. Okay? So here I just give you an example, right? This is a very simple example. So in this case, we might assign each data point into one of the three groups. Okay, there are quite a few applications. So one of these clustering applications is so-called image segmentation. So the problem is, given an image, you want to assign each pixel into a group, right? You want to, categorize those pixels that look similar into a single group. Right? In this case, you have something like this. This is, in this case, it's unsupervised learning. But when you see, if you read some papers, when you see image segmentation, they might be referred to as another supervised image segmentation. It's called semantic segmentation. So there are two. The term image segmentation may be a little bit confusing here. But here we are talking about unsupervised learning. And if we have some data points in 3D in this case, right? We might be able to assign each data point into a group, and we can visualize the data in 3D. One more. Oh, sorry. So this plots, I just plot the pixels of the previous image into 3D, right? Because each pixel has 3 channels, so it's RGB. So you can plot the you just ignore the pixel location information and plot the RGB value in this 3D space. Okay, so after you do this unsupervised image segmentation, you can for each group pretty much you can just store one set of RGB values, right? So in this way, you can compress the images. Right? But then, okay, we say that the criteria is to group the data points into a few different categories, a few different groups, right? Such that the data points within one group look similar. The distance between one group should be small. Then, same as in the case of k-nearest neighbor. Recall that when we studied the k-nearest neighbor, we say that you first need to define a distance function, to measure the similarity or dissimilarity between pairs of data points. Here it's the same, right? We need to define a distance function first, right? Such that we can calculate the distance or the dissimilarity or similarity between samples. And we also need to have an objective function to measure the goodness of the model, right? And once we have the objective function or the loss function, we need to have an algorithm to minimize this loss function. So that's the key component of data clustering. The first algorithm we're going to talk about is so-called k-means clustering. as the name suggests, you might, understand that there must be some similarity, some connection between k-means clustering and k-nearest neighbor classification. Actually, at a high level, these two algorithms are, indeed share some similarities. Okay, so let's first talk about the distance functions, right? Again, same as in the case of k-nearest neighbor classification. That's the first thing we need to do. So the choice of this similarity function, it's task dependent, it's data dependent, right? So you can consider, the types of the features, and it's also possible to learn the distance function. Again, that's the same as in the case of k-nearest neighbor, but we're not going to talk about how do you learn a distance function in this course. This is, to learn the distance function for k-means or k-nearest neighbor classification. It's an ongoing active research topic. You can find, tons of papers talking about that. It's unsolved. So the first distance function, you might think of is, of course, the most popular, the standard one, right? The Euclidean distance, the L2 distance. And when you use this kind of, the Euclidean distance function, either for k-means clustering or for k-nearest neighbor, you assume the data within the class follows a unimodal Gaussian distribution, right? But it's not always the case. So if the features have different scales, what you can do is you normalize the data before you run the algorithm. So this figure just shows you an example of the left plot is the original data without normalization, and the right one is after the normalization. So there are a few different ways to do the normalization, the data normalization, right? The most popular one is you can say minus the mean of the data and divide each feature, each dimension of the data with the variance of the data. Right? So you calculate the mean and variance first. Or you can do, for example, you just run a PCA on the data. Right? That's just another type of normalization. Right? Hopefully you can just reduce some of the noise in the data. But it's not always helpful. So again, it's a data dependent. Right? Sometimes, if you run a normalization, if you apply normalization to your data, the k-means clustering performance might be even worse than you not do it. Right? Okay, so that's the distance function. So in the case that you don't have any prior knowledge about the data, it's typically you just use the Euclidean distance as the distance metric to calculate the distance. Right? You can also use L1. So the L1, L2, these are the most widely used distance functions. All right, so now let's talk about k-means. There are quite a few different clustering algorithms. So k-means probably the most, the most popular one, also the simplest one. Then we also have the Gaussian mixed model and k-medians and hierarchical clustering, spectral clustering. But we're not going to cover all of this algorithm. We mainly focus on k-means and mention a little bit about the Gaussian mixed model. Gaussian mixed model is actually very useful, not just for clustering. It's also one of the main algorithm to do the density estimation, right? To model the density of the data points, all right? In many cases, in Bayesian analysis, you need to estimate the data first, estimate the density of the data first. And in that case, usually we just use Gaussian mixture model. Okay, so let's check the idea of k-means. It's very simple, right? If you recall, how we apply this k-nearest neighbor to the classification, then k-means is just a very, very simple extension to the, in some sense, to the k-nearest neighbor. Okay, so the purpose is we need to find a, prototype. Here we just use the symbol mu k, right? So let's assume we want to group the data into k different groups, okay? So we need to find the k prototype mu k. Here, prototype just means, the representation, okay? In this case, it's just the mean of each subgroup. So it's we need to find the k center of the k subgroups, right? One center for each, or centroid for each subgroup. And once we have the prototype or the center or the representation of each subgroup, we can assign each data point xi to a cluster, right? We can define indication variable here. Rik is just the indication variable. It's either 0 or 1, right? So each data point in this case can only be assigned to one subgroup, okay? So here just an example of, let's say if we have 4 data points and 3 clusters, right? So here each row is corresponding to a data point, right? In this case, and each column is corresponding to the to a cluster, to a subgroup, okay? So the first element in this matrix, that means the first data point is assigned to the first cluster, right? And the second data point is assigned to the third cluster, right? And the third data point is assigned to the second cluster, and the last data point assigned to the third cluster again, right? So we can have once we have this indication variables, right? That means all the data points are assigned to one of the clusters. And then we can define the loss function, something like this, okay? So this is really just the sum of the distance of each data point, between each data point and its corresponding prototype, right? So we have k clusters or prototypes, right? So mu k is just the prototype, and xi, only if xi is assigned to cluster k, this is 1. Otherwise, it's 0, right? So that's the the whole distance of each data point, between each data point and its corresponding prototype. Okay? So this is the object function we want to minimize, right? So it looks like it's not easy to optimize this, to directly optimize this object function. Why is that? Because we have a discrete variable here, right? This is either 0 or 1. It's binary. So we have a discrete, variable. And, this problem, this minimization problem, if we want to minimize J, the loss function, overall it's NP hard. The object function itself is non-convex, right? And it's NP hard to find the globally optimal solution. So we can only find a local solution, local optimum, just because of this, because of this discrete variable, which makes the problem very, very difficult. So just observe that we have two sets of variables, right? One is the prototype, right, or the center for each cluster, and the other one is here we call it responsibilities, or it's just the indication variables, right? So we have two. So and it's a chicken and egg problem. If we know the prototype, then the indication variable are very easy to calculate, right? You just given a data point, you just calculate that data point, the distance of that data point against k prototypes, and pick the minimum one, right? And assign that prototype to this data point. It's like a k-nearest neighbor, right? And if the indication variable or the responsibilities are known, and then we can just calculate the prototype. In this case, it's just the mean of each cluster, right? It's very simple to calculate the mean. So it's really it's a chicken and egg problem, and this inspires us that we can solve the problem using an alternative optimization technique, which is we can iteratively solve the problem by fixing the prototype, solve for the responsibilities, the indication variables. And the next step is you fix the indication variables and solve the prototype, right? Just calculate the mean of each cluster. And that's how we do it. Okay, so it's very simple, right? So we have two steps. Here we just slightly abuse the notation. It's not really EM, right? We're going to talk about a little bit about EM, but it's just we have two steps. One is fix mu k, which is a prototype, minimize J with respect to the indication variable. That's very simple. You just just assign each data point to its nearest prototype. And the second step is fix the indication variable and minimize object function with respect to the prototype. And in that case, you just calculate the mean of the data points in that cluster, in that subgroup. Okay? So it's very simple. Here, sum I, r, I, k. This is a number of the data points in that cluster, right? And then you just iteratively run the algorithm. This procedure is guaranteed to converge, but it only converges to a local optimum. Okay, it's not guaranteed to converge to a globally optimal solution. Right? You can only find a local solution. Okay, so it converges to a local minimum. At this stage, you might ask a question because it's a chicken and egg problem, right? So how do you start? How do you initialize the solution, right? If we start from this E step, right, you need to fix the prototype. How do you get to the prototype, right? You have to initialize the algorithm before you run this iterative optimization procedure, right? The simplest way to do this is you just randomly pick k data points as the prototype, as the value of mu k here. Okay, that's the most popular way to initialize, and they are not. There's no better way to initialize the algorithm, right? So, but one thing you can do is because the optimization algorithm converges to a local solution, right? So it actually, the final solution depends on the initialization, the value of mu k here. So one thing you can do is you can run the algorithm multiple times by choosing different initialization, and then pick the best one. Here, because we have the objective function, right? You can pick the solution corresponding to the smallest objective value. But again, this is the objective function is NP hard, so it's not to find the globally optimal solution is very difficult, right? It's the computation complexity is exponential to the number of the variables, right? So there's no polynomial time optimization algorithm to solve for the globally optimal solution. So there's some heuristics. As I said, the most popular one, you just randomly pick the data points as a prototype for initialization. But you can also say pick the I+1 prototype to be the farthest to the already picked prototypes. But again, it's not guaranteed that this strategy is better than a pure random selection. Okay, let's see some examples. If we have such data set and we want to run the algorithm on this data, let's say, again, I forgot to mention. So because this is called k-means, right? So how do you pick? How do you select the value of k before you run the algorithm? It's the same as in the case of k-nearest neighbor, right? As I said, in k-nearest neighbor, you need to somehow to determine the value of k before you run the algorithm. Here, we also need to determine the value of k before you run the k-nearest neighbor. There's no, a very good solution to find the optimal value for k. You can only using, for example, cross validation to find a good k. Right? You can run the algorithm. You can try different k and run the algorithm multiple times, and select the best model. So again, it's heuristic. There's no a good way to find the value of k. Okay, so if we pick these two as the prototype, then the first iteration will give you something like this. Okay, that's the first iteration. So obviously, those data points above this straight line will be assigned to this prototype, and below the line will be assigned to this prototype. Right? This is the first iteration. And then we recalculate the mean of the two prototypes, of the two clusters. And that's the updated prototype after the first iteration, right? And we do it again. We just reassign each data point to these two prototypes by calculating the distance between each point and the two prototypes, right? Okay, then that's the after you recalculate the assignments, right? We assign all of these data points to this prototype, and all of these data points, red points, to this prototype, right? And we can keep doing that. After a few iterations, it will converge, right? That's the updated prototype, right? And you do it again. That's the new assignments. Okay, and then this is the updated prototype. So at this point, you can see actually the results make sense, right? You can see that the data points are grouped into two clusters, and you can do it. And then this is the if you plot the loss function, the object function against each iteration, you get something like this, and that's after the full iteration. And it looks, just check this curve, right? It looks like it's converged now, which means, well, upon convergence, which means if you run the algorithm more iterations, the result will not change. Okay, the loss function will not decrease again. Okay, so I mentioned how do you choose k? This is same as the choosing k in k-nearest neighbor. The loss function j generally decreases with k, right? That's something pretty obvious, right? In the extreme case, if each data point is a subgroup, right? Each data point is a prototype, then the loss function is 0, right? But that's meaningless, right? So one thing is if you choose different k and you run the algorithm, you check the loss function, you might see a gap between the loss functions corresponds to different k, right? But the most common one is, as I said, you can use cross-validation. And you may also check the stability of the clusters, which is to measure the change in the clusters obtained by resampling or splitting the data, right? And there are some other non-parametric approach. For example, you assume a prior distribution on the k, right? And another thing you can do is you just increase k by 1, right? Let's say you start from k equals 2, and you run the algorithm, and you use that result. Well, after you run the algorithm, you will get 2 prototypes, right? And then you set k equals 3, and you just randomly pick another prototype and run the algorithm again. So it's like incrementally learn the clusters, and then you can in this way you might get a better solution. Right? Then you just randomly pick k and run the algorithm. But again, all of this are just heuristic, right? There's in general, this is a very difficult research problem. To how do you pick the optimal value for k? Okay, so some drawbacks for this k-means algorithm. Again, same as in the case of k-nearest neighbor. So we actually just use the hard assignments of data points to clusters, and this might cause a small perturbation to a data point to flip into another cluster, right? So there's no probability. Just imagine, what if a data, let's check the previous example here. Say, what if some of this data are just kind of on the boundary of the two clusters, and you have to make a hard decision, right? In theory, those data points kind of on the boundary should be 50% on the cluster 1 and another 50% on the cluster 2, right? It should be soft, right, instead of hard. So, so in this case, we can use this Gaussian mixed model. That's the second technique we're going to cover today, right? In the case of Gaussian mixed model, each data point has a probability, right, of being assigned to a particular cluster. And if we use the Euclidean distance to calculate the similarity or dissimilarity between pairs of data points, then we assume, spherical clusters, right? And an equal probability for each cluster. In reality, this assumption may not hold, okay? Again, we can use Gaussian mixed model to relax this assumption. And the clusters may change arbitrarily for different values of k, right? Even k is, let's say, incremented by 1, the result will be, drastically different. Right? That means the algorithm is not actually very stable in terms of the value of k. Right? And in that case, we can sometimes use so-called hierarchical clustering. That's a more sophisticated clustering algorithm. And it's sensitive to outliers, as you can imagine. Let's say if you have an outlier which is far away from all the other data points, and you have to consider, when you calculate the prototype, the means for for the subgroup, for the cluster, and that far away outlier will affect the calculation of the value of the prototype, right? Will pull away from the pull the prototype away from the true data points, the true location of the prototype, right? And it will give you a wrong solution. And in this case, we might use a robust loss function instead of just calculate the sum of the overall distance. And because we are assuming, well, a Gaussian distribution for each cluster, right? And if the data points of some clusters are actually non-convex, right? Not to mention it's a Gaussian. Of course, a Gaussian distribution, right? The shape will be convex, right? If it's not convex, then it will fail. Right? And in this case, we can use so-called spectral clustering. The high-level idea is to map the original data into a higher dimension, such that in that high dimension space, the data points will be convex. Okay, the shape of the cluster will be convex. Sorry. Okay, so there are quite a few different, more sophisticated clustering algorithm than the k-means clustering algorithm. But we don't have time to introduce all of them, right? So the second important clustering algorithm is Gaussian mixed model. And as I said, the GMM, or Gaussian mixed model, besides clustering, it's also a very important probability or density modeling technique. Right? You will see Gaussian mixed model frequently in the machine learning literature. Okay, so it's actually it's a very simple extension to the k-means, right? If you understand the k-means, then pretty much the Gaussian mixed model is to relax the hard assignment. Okay, we just instead of using a 0, 1 indication variable, we use a continuous variable. Right? So mathematically, we have such a model. Okay, so each cluster is associated with a Gaussian distribution. We assume a Gaussian distribution for each cluster, and it's not necessarily spherical Gaussian. Okay, which means at each direction axis of the Gaussian distribution, the length of the axis might be different. Right? It's not a spherical. Instead, it's well, in 2D it's an ellipse. Okay, in high dimension it's an ellipsoid. Okay, we don't assume it's a spherical distribution, Gaussian distribution. And to generate data, randomly choose a cluster K with probability pi k and sample from its distribution. Okay, that's the probabilistic explanation. All right, so it's just we have a bunch of data, and those bunch of data, of course, will follow distribution, right? A probability distribution. And then in this case, let's assume the probabilistic distribution is a Gaussian mixed model, right? And this is a formulation of a Gaussian mixed model, right? That's the distribution of X, okay? And this mixture, you see, it has K Gaussian distributions, right? And this is the weight for each distribution. And in this case, of course, it must sum to 1, right? The sum must be 1, right? So pi k itself is a probability, okay? And if we sample the data from this distribution, we might get something like this, right? Here, just give you an example. We have 3 Gaussian distributions. And if we sample from this Gaussian mixture model, we get the sampled data. If we plot the sampled data, we get something like this. Can anybody tell me how do you sample from a Gaussian mixture model? Well, I already said in this slide, right? So the first, there are two steps. Step one is you just choose a cluster K with probability pi K, right? Because each pi, right? Let's say if K equals 1, in this case, K equals 3, right? You have pi 1, pi 3, pi 2, pi 3, right? And pi 1 plus pi 2 plus pi 3 will equal to 1, right? And you just, with probability pi K, you pick a cluster. And once the cluster is determined, you just sample from Gaussian. Sample from Gaussian is very simple, right? Okay. And same as in the case of K-means, we need to define the loss function, right? And the loss function is the negative log likelihood if we want to minimize this loss function. This is equivalent to maximum likelihood estimate, okay? The loss function is actually to maximize the likelihood, right? Why to maximize the likelihood? Just recall in the first lecture we talked about prior likelihood and posterior, okay? And in this case, and as I said, in a Bayesian framework, in most of the cases, you want to have the MAP estimate, the maximum posterior. And because we don't have any prior, so we assume a uniform prior. In this case, MAP, maximum posterior, equals to maximum likelihood. Okay, so in this case, we just in order to estimate the parameters, we just maximize the likelihood, and to maximize the likelihood is the same as minimize the negative likelihood. Okay, so that's why we are minimize the negative likelihood. But hold on, we have a log here, right? Why we have a log here? And impose this log. What's the effect? The impact of this log calculation. Sorry? Yes. So to convert the product into sum, right? But why we can do that? Why can we just apply a log? Can anybody tell me? Or any of you actually thinking about that? Okay, so the underlying reason that we can just apply log to the object function is log is a convex function. Okay, log is a convex function. So if you apply the log, say if you want to minimize fx, but instead you minimize log fx, you get the same solution, right? Log is a convex function, and you apply log does not change the value of the object, changes the solution to the optimizing problem. It does change the object value, of course, right? But it will give you the same solution, right? Just remember that. If you can always apply a convex function to a minimization problem, and the solution will be the same. Okay? And in this case, as he said, you actually change the product into sum, which makes the problem easier, makes the optimization easier, right? So if you don't have this log, this sum will be a product, okay? Instead of sum from I equal 1 to n, you actually calculate the product from I equal to 1. So now after you apply log, you just change the product into sum. All right, so now we have the objective function or the loss function, right? So to estimate the parameters, all we need to do is just to minimize this negative log likelihood, which is the same as maximize the likelihood. So it's difficult to optimize, same as in the case of k-means, right? As I said, in the k-means, it's the objective function is a little bit difficult because we have these two sets of variables. You have the chicken and egg problem, and one of the variables, the indication variable, is discrete. Here, we can see that the sum over the components appears inside the log, and it's coupling, all the parameters, right? So now each xi, so we also have this so-called chicken and egg problems, right? Same as in the, so different from the case of k-means. In the case of k-means, each xi, here xi is a data point, right? Each xi is only assigned to one cluster. But now, in this Gaussian mixed model case, because the assignment is soft, right? So each xi has a probability, which is a probability that this particular xi belonging to a particular cluster, right? If we have k clusters, for each data point there's a k probabilities. So we can introduce a so-called latent variable z, okay? So this we have for each xi we have k z, all right? So now, given the complete data x and z, remember the physical meaning of z. Z is a probability of this xi belonging to a cluster. So we can estimate the parameters by maximizing complete data log likelihood, okay? So now the pi k and the variable, the parameters for each Gaussian is decoupled, okay? So by introducing a latent variable, we reformulate the original loss function. Okay, but we need to calculate the we need some way to calculate the probability zk, right? What we can do is we use we'll fill in the latent variable using the current estimate of the parameters. It's the same as in the case of k-means, right? You just fix one set of variable and optimize for the other set, right? And then adjust the parameters based on the filled-in variables. Okay, so now we have, just check the case for k-means. We also have two steps. One is E step, and the other one is M step, right? E means expectation, M is maximization, right? So given parameters, we can compute this is the assignment, right? And then maximize the expected complete log likelihood. You maximize this one. And the second step, actually, it turns out there's a closed form solution. So you can update the parameters pi k, mu k, and sigma k in this way. Sigma k is the covariance matrix for each Gaussian. Mu k here is just the mean, okay? And pi k is the weight for each Gaussian. Here, the RIK, just recall, in the case of k-means, it's the assignment variable, right? In the k-means case, it's an indication variable. But now, it's a probability. It's not 0 and 1, right? For each component of RIK, because we have, for each I, for each xi, for each data point, we have k dimension, right? For each dimension, it's a value between 0 and 1, right? Okay, so this is the, then the rest of the optimization is the same as in the case of k-means. You just run the algorithm iteratively, and at the end of the day, it will converge, okay? But again, it only gives you a local optimum, right? It will not, you will not be able to find the globally optimal solution, right? So this is the EM algorithm. EM algorithm is a classic optimization strategy for quite a few different parameter estimation problems in statistics. And in this case, we just apply EM algorithm to estimate the parameters in Gaussian mixed model. The good thing about this is the second step, right? The maximization step, you have the closed form solution for pi, mu, and the covariance matrix, right? That makes the computation much more efficient. If you are interested, I actually already uploaded a document to the discussion section of the course forum. You can check that document. But it involves some mathematics, right? I encourage you to read it, but I don't expect all of you can understand, every detail of the EM algorithm. So if you don't understand, that's okay. As I said in the discussion, it will not be in the final exam for the EM algorithm. By the way, you don't have to use EM algorithm to estimate the parameters of Gaussian mixed model. Because, why is that? Because at the end of the day, let's check this. Okay, let's check this problem, right? So we just need to, in this case, just minimize the negative log likelihood or maximize the likelihood, right? We already write this object function. So, can you think of some other algorithm which can give you the solution if you want to minimize this problem? Right? The first thing you might try is gradient descent. Right? That's the simplest optimization method. Right? You can and you can always calculate the gradient given this objective problem. Right? You can just calculate the gradient with respect to pi, mu, and sigma, and then just run the gradient descent to find the solution. So EM algorithm is not the only option, right? As I said, because for the EM algorithm, you have for each iteration you have the closed form solution. Okay, So it's very efficient. One thing I want to mention that if you don't use EM and instead you use gradient descent to update all the variables, one small problem you need to be aware of is this sigma k. Sigma k is a covariance matrix, right? And just a couple weeks ago, I said one property of covariance matrix is it must be positive semi-definite, which means all of its eigenvalues must be non-negative. And if you use gradient descent, just remember the key idea of gradient descent. For each variable, you just update it by a small, it's like a perturbation, right? X equals x plus delta x. Delta x is the gradient, right? And then you need to be careful because for a matrix variable, if you plus or minus another matrix, it may give you, it may result in a, non-semi-definite matrix, okay? Unless, well, if the sum of two semi-definite matrices must be semi-definite, right? But if one of the matrices is not semi-definite, then the sum of the minus will not be semi-definite, right? And that causes problem. So if you use gradient descent in this case, you have to project the matrix back to the semi-definite space, right? And that can be slow. Okay. But anyway, the take-home message is EM is not the only option to estimate the parameters of a Gaussian mixture model. And actually, if you have a very large data set with high dimensional data, EM algorithm may be computationally too expensive, okay? So in that case, you might have to use gradient descent. Although the convergence speed of gradient descent is slow, it does have the advantage of being capable of dealing with large scale data set, right? In some sense, the gradient descent is a first order optimizing method because it only involves the gradient, right? It does not involve second order or high order statistics. And the EM algorithm can be sort of second order, actually not exactly second order, but like a semi-second order optimizing problem. The convergence speed is faster, but it may not be able to handle large scale data set, okay? All right, so at this point, I guess you guys do see the connection between k-means and the Gaussian mixed model, right? The E step in Gaussian mixed model is a soft version of the k-means, okay? In the case of k-means, the integration function RIK is either 0 or 1. No, it's a probability. It's a value between 0 and 1, right? And the M step, the maximization step in Gaussian mixed model estimates the probabilities and the covariance matrix of each cluster in addition to the means. In the k-means, you only calculate the means, right? Now you have the covariance matrix, which determines the shape of the ellipse. And all pi k are equal. If all pi k are equal, sigma k is identity matrix. And let's assume the scale of the identity matrix becomes becomes 0, which means you don't consider the covariance matrix, right? And then RIK, the indication function, will become discrete. Then this Gaussian mixture model will the same as the K-means. Okay, so in some sense, K-means is just a simplified version of Gaussian mixture model. And because of this connection, in Gaussian mixture model parameter estimation, sometimes we can just run the K-means first, and using the result of the K-means as the initialization of the Gaussian mixture model, the EM algorithm for Gaussian mixture model. Okay? And sometimes this using the K-means as a initialization, K-means result as a initialization will give you better estimate of the parameters than you randomly initialize the EM algorithm. Okay, let's see some examples. So this is the same data set as we showed, right, before. So now this is the initialization. Well, remember in the case of K-means, it's we just initialize the K-means with 2 prototype, right? It's just the mean of each cluster. But now, besides the mean, we also need to have the covariance matrix. So that's why it's not a single point. It's in this case, it's a circle because we assume the covariance matrix is spherical, right? Which means for each axis, the length is the same. And after the first iteration, we get something like this, right? The different color just encode the assignment of each data point. And then we recalculate the covariance matrix and the mean. Then the 2 Gaussian becomes something like this, okay? And again, the different color is the indication of the assignment. And we run the algorithm again. And after this is the result of after 5 iterations and 20 iterations, we get something like this. Okay. So now you can see that after 20 iterations, you can see that each data point is correctly assigned to one of the 2 clusters. And this is a covariance matrix after 20 iterations. Okay, so this is the comparison between K-means and the Gaussian mixture model. Right. So the loss function, of course, are different, and K-means use harder assignment, and the Gaussian mixture model is soft assignment. And the K-means assume spherical clusters with equal probability of a cluster. And the Gaussian mixture model can be used for non-spherical, like ellipsoid clusters with different probabilities. Okay, so the last clustering algorithm I want to mention a little bit is the so-called K midpoints. This is just a very simple modification to the K-means. Okay, only a small modification. So we mentioned that the squared Euclidean distance loss function of K-means is not robust, right? It's very sensitive to outliers, right? Just imagine if there's an outlier point which is far away from the other data points, then when you calculate the mean, the average of a subset of the points, the average, the mean will be like, pulled away from the true estimate, right? And what if we change the way that you calculate the prototype or the mean? Okay. So instead of, well, the first thing we do is instead of using the L2 loss function, we can use L1 loss function, right? Remember, in the original k-means, it's L2. Now we can use L1, right? And in general, L1 loss function is more robust to the L2 loss function. And then we just still use the iterative procedure as in the case of k-means, right? But now the prototype is the median of the data points, right? Instead of the average, right? So that's the only thing we modify. Instead of calculating the mean, now we calculate the median, right? So well, I just assume everybody knows the definition of median, right? The median is the value in the middle, okay? Not the average, not the mean, not the average, right? You just pick the value. Let's say if we have 3 values, 1, 2, 5, then the median is 2, right? Just the number in the middle. That's the median. But if you calculate the mean of 1, 2, 5, it's 8 divided by 3, right? So these two values are different. And just imagine, let's say the third number is the outlier, okay? And it's far away from the first two. Let's assume the third number is 100. So now you have 1, 2, 100. And if you calculate the mean, that's 103 divided by 3, right? But if you calculate the median, it's still 2, okay? The median remains unchanged, right? So that's why in some of the cases, if you have outliers, the median will be much more robust than the average, right? Okay, so that's all we want to talk about today. And if you are interested in this clustering methods, you should check this book. Well, the book I recommended in the first lecture, The Elements of Statistical Learning. Just download the PDF from the author's website. Just read the first one will be good enough. Okay, so that's all for today. So next week, we will go back to classification, where we'll talk about boosting algorithm, which is example of ensemble learning. And in particular, we will introduce the algorithm called AddBoost. And just same as supported vector machine, AddBoost is another very important classifier. And the second assignment, which will be released next week, is to ask you to implement AddBoost. Okay? And you can probably compare AddBoost with, say, SVM. All right, so that's all for today. Any question before I go? All right? Okay, so that's all good.
Can I ask the assignment one?
Yes.
I already coding my project, and the accuracy of my classification is 90%, but
Yeah.
I'm not sure.